So do we start now? Right, so good morning, everyone. I'm Ewelina from British Geological Survey, and thank you so much for inviting me to present today. I would like to introduce you all to the idea of space weather and space climate. In other words, what actually happens between us on Earth and the Sun. So what exactly is space weather? Space weather is a field of physics which describes the conditions within our solar system, especially between us on Earth and the Sun. It all starts with our dynamic and extremely complex star, the Sun. Even though it's 150 million kilometers away from us, we can see its effect on the Earth all the time. The Sun is constantly emitting radiation and particles from various places on its surface, which travel all across the solar system in the form of what we call the solar wind. Now, let's have a closer look at our main suspects today. As you may or may not know, the Sun is not just a bright and uniform sphere in the sky. It has many dynamic features that can change from day to day, and thanks to many different satellites and other observational techniques, we can observe the Sun basically 24/7. Let's start with coronal holes. As you can see on the picture here, they are those dark areas on the solar disk that appear dark because they are cooler and less dense than the areas around them. Coronal holes are especially dangerous to us because they are a region of open magnetic field, which allows the solar wind to easily escape into space and travel at very, very high speeds. Coronal holes can appear at any time and usually last for several days before either closing up or rotating away. Solar flares, a bit more exciting than coronal holes in my opinion. As the name suggests, they are sudden and quite large explosions of electromagnetic radiation from the Sun, usually lasting for a couple of minutes or, in very bad cases, for several hours. Opposite to coronal holes, which effects can be visible on Earth after a day or two, solar flares can have immediate impact on the side of the Earth that is facing the Sun, since they travel at the speed of light. Solar flares appear in active regions formed by sunspots with strong magnetic fields. So what are those sunspots that I just mentioned? They are temporary dark spots on the surface of the Sun, which appear in regions of strong magnetic field, which keeps the heat trapped inside the Sun. Just like coronal holes, they are dark because they are colder. Although they look fairly small on the picture here, some of them can become many times bigger than the Earth. Sunspots are quite social and like to group together in what we call active regions. The number of sunspots we get depends on where we actually are in the so-called solar cycle. Solar cycle is often used to describe the level of solar activity. It is estimated by the number of sunspots visible on the surface of the Sun. Over many, many years of research, it has been found that each solar cycle lasts for about 11 years and can be separated in the solar minimum, with low number of sunspots and mostly quiet conditions, and solar maximum, vice versa, plenty of sunspots and high activity on the Sun. We are currently at the beginning of the solar cycle 25, which is predicted to be relatively quiet compared to previous ones. Now, time for my absolute favorite, coronal mass ejections, CME for short. Again, fairly self-explanatory. Those are the massive explosions of plasma and magnetic field from the Sun's corona, where billions of tons of solar material are ejected into space. CMEs can come in different shapes of sizes. One can travel slow at about 250 kilometers per second, but another one can explode with a speed as high as 3,000 kilometers per second. Depending on their speed, CMEs can arrive at Earth in less than a day, but in most cases, the arrival is seen after a couple of days. Usually when they arrive, they can disturb our magnetosphere, causing a geomagnetic storm. More about those in a minute. On the left-hand side is an example image taken by the LASCO instrument on SOHO satellite during the famous event from September 2017. Here we can see the same coronal mass ejection in its full glory. The black circle in the middle is the Sun, which is shaded to showcase only what happens in the corona around the Sun. This event is what we would call a full halo CME. As you can see, the ejected material covers the sun in almost a full circle. This means it was traveling directly towards the Earth. Okay, now that we know the basics of the dynamics of the sun, let's look into what happens between us on Earth and the sun. First things first, we need to understand what is the geomagnetic field of the Earth. It's the area around our planet where the magnetic force dominates. It is mainly generated by the molten iron in the Earth's core, which is slowly moving around. But sources found in the crust layers and the ionosphere also contribute to the overall geomagnetic field force. This field is not constrained only to the Earth's interior, but extends far into space as well in the region known as the magnetosphere. I would also like to quickly point out that the magnetic North Pole is located at the geographic South Pole and vice versa. That is why compass points always to geographic north, since the opposite attracts and the needle in a compass faces the direction of magnetic South Pole. Like I mentioned before, solar wind is constantly traveling through space, either from coronal holes or coronal mass ejections. Thankfully, the Earth has a protective shield covering us from harmful solar wind and radiation. We call it the magnetosphere. It's a comet-shaped bubble that surrounds our planet, created by the Earth's own magnetic field. The image on the bottom shows that our magnetosphere is always compressed on the day side, facing the sun, where the pressure of solar wind is stronger than our magnetic field. That's where the interactions usually happen. I previously mentioned a phenomenon known as geomagnetic storm. So what is it exactly? Magnetic storms are periods of major disturbance in our magnetosphere caused by the interaction with strong solar wind, most often after a big coronal mass ejection or the arrival of coronal hole fast winds. Usually, magnetic storms last for a couple of days and vary in intensity. The animation on the right shows how our magnetosphere interacts with the solar wind. As the wind arrives, the magnetosphere gets compressed on the day side, here on the left-hand side. Then, as the magnetic lines broke, they escaped all the way to the night side Earth, where they connect back together. During that reconnection, all of the solar particles travel along the field lines down to the ionosphere and then atmosphere. When this happens, if you look closely at the poles here, you can see a nice light forming. This is the famous aurora. Aurora, or northern lights, are pretty much the only relatively good effect of geomagnetic storms. Like I mentioned, aurora are the results of solar particles traveling down to north and south poles along the magnetic field lines. As they interact with gases in the atmosphere, we see beautiful displays of colors in the night sky. Oxygen produces green and red, and nitrogen gives blue and purple tones. When you think of the northern lights, you probably think of Iceland or Norway, but they can sometimes be seen even in the UK when the geomagnetic activity is high enough. The photo at the bottom left was actually taken by one of my colleagues recently in Scotland. We've talked about all the nice things that space weather brings us. However, most of its impacts are rather unpleasant, to say the least. Space weather and geomagnetic storms cause major radiation hazards, especially for astronauts on space missions, but also for airplane passengers flying at high altitudes or around the poles. When we have a strong enough storm, satellites can be damaged or even destroyed. That satellite damage can then result in GPS and navigation failures and also disturb radio reception. Another negative effects of space weather can be seen on ground level within power grids. That's the area I'm most interested in, actually. The rapid variations in the magnetic field during space weather storm creates dangerous electric currents flowing in the ground. When those currents find a power network line, they like to travel within it, causing major interference or total distractions of part of the network. This can result in electricity blackouts for many, many hours. Now you may ask, how do you predict space weather to avoid such awful effects? Here's a really basic forecasting process we follow every day at British Geological Survey. First, we like to start with just having a quick look at the surface of the sun, usually using the Solar Monitor website, where you can view all of the different images taken by satellites. This gives us a general idea what we can expect in terms of solar activity. Next, we would like to double check if there are any coronal holes currently present that might be facing us on a given day. There are many sources of coronal hole maps. Here's just one of the examples we use at BGS. After that, we will have a closer look at actual measurements taken by satellites. In this example here, we're looking at the X-ray flux, which tells us if there are any significant solar flares in the last couple of days. Solar flares can be separated into different categories called A, B, C, M, and X. If we see a spike reaching the M or X value, that's when we would start to panic. Another thing that we constantly check are the solar wind data measured in real time by satellites placed in between the sun and the Earth. Those include the solar wind density, speed, temperature, and its magnetic field values and orientation. The last one is particularly important since geomagnetic storm only truly affects the Earth when the solar magnetic field is facing south. Last honorable mention are various models used to predict the behavior of the solar wind. In this picture, we see the Enlil model that produces estimates of both density and speed of the solar wind at Earth several days in advance. Oh, another thing that I simply couldn't fit on the slide here are videos of the sun, just like the one I showed you before. This shows us any potential coronal mass ejections that might be heading our way. With all that in mind, we can then proceed to do our daily forecast. First things first, there is a universal planetary KP index commonly used to determine the expected level of geomagnetic activity. It is based on magnetic measurements taken every 3 hours from 13 observatories at middle latitudes. It ranges from 0 to 9, where 0 indicates quiet conditions, and anything 5 and above indicates a geomagnetic storm. On the right-hand side is an example plot reproduced in real time with the estimated values of KP on a given time period. In this case, the September 2017 storm again, which reached maximum KP of 8, meaning very, very big storm. Okay, now that we know what KP index is, how do we use it in our space weather forecast? Like I just mentioned, anything with KP above 5 indicates a storm. However, geomagnetic storms vary in intensity. Therefore, the space weather scale introduced by the National Oceanic Atmospheric Administration, NOAA, is often used to predict the anticipated level of activity. It goes between G5, G1, and G5. The table here shows the possible impacts of each activity level. As you can see, G5 geomagnetic storms can be really dangerous. Thankfully, they don't happen very often. Not yet, anyway. With all that in mind, the forecast can be then prepared. Here's an example forecast provided by one of my colleagues back in September 2017. As you can see, we got it almost correct that time, predicting the maximum activity reaching levels of storm G3, and then slowly decreased to maximum of storm G1. Those forecast messages are sent out every day, giving 3 days in advance warning to our customers. Of course, just like in terms of normal weather, it's rather difficult to get the forecast 100% correct every time. But as more research and more data are becoming available, we are getting closer and closer to increasing our predictive abilities. Last but not least, I would like to point out a few sources of space weather information provided by British Geological Survey. Those include the already mentioned daily forecasts, but also our Twitter accounts, BGS Space Weather and BGS Aurora Alert, and BGS Space Weather Alerts webpage. When the forecasted activity is expected to reach high levels, an alert is sent to our subscribers, informing them of chances of seeing aurora in Scotland or Northern England. Anyone with an email address can subscribe, so if you're interested, feel free to give it a go. Okay, I think I've rambled for long enough, so let's see how much you actually remembered. I think you can access the quiz questions via Menti. The link was provided before. If someone can say something. Okay, here's the link again, if you want to scan the code. So first question, how long is the average solar cycle? 11 years, 22 years, 28 days, or 1 year? Okay, I think I've been told everyone thinks it's 1 year. Well, unfortunately, it's actually 11 years. Okay, let's move on to the next one then. Why coronal holes appear darker than the surrounding areas? They are warmer and more dense. They are colder and more dense. They're colder and less dense. So if anyone voted for colder and less dense, you are correct. Okay, so what do we call a massive plasma explosion of the sun? The solar wind, coronal mass ejection, or solar plasma eruption? My absolute favorite again, coronal mass ejections. What protects our planet from the solar wind? The moon, International Space Station, or the magnetosphere? And of course, the answer is the magnetosphere. The planetary KP index varies on a scale from 1 to 5, 0 to 9, 0 to 10, or 1 to 100. And the answer is 0 to 9. Okay, that's all from me. Here are some resources and references, and happy to answer any questions. Okay, so the first question, what's your favorite part about working with space weather? Oh God. I remember being at uni for the first year, and we were studying about all those weird concepts of space and everything. And now I can actually see how I can apply them in real life. And before starting working with space weather, I had no idea how dangerous it can actually be. So being able to help provide the forecast is actually very rewarding. Okay, next question. Where can you see the Northern Lights in Scotland? My colleague went to the Isle of Harris recently. The picture I showed you was taken actually there. But sometimes when the activity is very, very high, I remember my other colleague telling me that she saw Northern Lights in Edinburgh actually. And sometimes they can be seen even as far down as Nottingham and that area as well. But it's very, very difficult to see them with just your eyes. You need the camera to properly see the green hue in the sky. What are the best conditions to see the Northern Lights? Like I just mentioned, it's very, very difficult to see them with just your eyes. But of course, you have to be far away from cities and like the city lights and stuff. So it's best to go in an open field with a good camera during the night to see the Northern Lights in full glory. Usually it's in Scotland, for example, it's really just that green hue in the sky, but it's still very exciting. Any more questions? Oh, and of course, if you want the best chances to see the Northern Lights, feel free to subscribe to our Aurora alert, and they will tell you 3 days in advance where to actually go and see them. How can we find out more about space weather? There are, honestly, just Google space weather. There are many sources, a British Geological Survey or NASA and ESA websites. Do you ever look beyond our solar system? Oh, no. That's too complicated for my brain. What is your favorite space fact? Oh gosh. Honestly, not sure. There's just too many. Yeah, I'm not quite sure. Were you always interested in space? Not actually, no. I was always interested in physics and maths. I know, very boring, but I decided to study just physics, and then I realized, space is kind of cool. So I guess that was about 3-4 years ago. What subjects did you study in school? Okay, so I'm actually from Poland, so we have a kind of different system. But in the secondary school, I studied physics, maths, And then I moved on to university here in the UK, and I studied physics with planetary and space physics. So that's the main subject. Does it rain in space? It's not that kind of weather, unfortunately. I mean, if you count solar particles, then that can be kind of rain, I suppose. Okay, I don't think there's any more questions. So again, thank you very much for listening to my rambling. And yeah, enjoy the rest of the event. Thank you so much.